Okay, and our final detail in graph theory is about finding that optimal solution when it comes to trees, okay, when it comes to spanning trees. So, spanning trees can also be used to find an optimal solution. And so, that optimal solution in this case is going to be called a minimal spanning tree. Okay, a minimal spanning tree is a spanning tree for a graph that has the smallest possible sum of weights. Again, whether that's a cost, whether it's a distance, whether it's a time, that's irrelevant. Okay, whatever the topic is, we want the smallest possible sum. And Kruskal's algorithm is what can be used for that. Okay, so we're going to walk through this next example. And again, I'm just going to read Kruskal's algorithm and we're going to walk through it one at a time. Okay, so step one, choose the edge with the minimal weight and highlight it. Okay, so looking at this graph, the edge with the minimal weight is the F to D with that weight of 12. And so we're going to highlight that. Okay. Then step two, choose the edge with the next lowest weight that has not yet been selected and highlight it. All right, so looking at the remaining edges there, 15 is the next smallest, and so we're going to highlight it. Step three, continue choosing edges in the same manner, except do not select any edge that will create a circuit among the highlighted edges. Okay, so we don't want any circuits. And we repeat that until all the vertices have been connected. All right. And there is a note there. If you have like more than one edge with minimal weight, let's say you had two that like, oh, it's a tie, you get to pick the one you want. Okay. You can pick whichever one. All right. So we've done a weight of 12 and a weight of 15. The next smallest weight is 19. Notice that will not create a circuit. So we're going to highlight that one. Looking at what's left, the next smallest weight is 24. Using the edge from B to C, that's not going to create a circuit either, so we're going to include that one. And then you'll notice there are two different weights of 25. There's that one right there and that one right there, okay? We cannot use the one from A to B because that would create a circuit, okay? So we're not going to use the 25 from A to B because, because that would create a circuit. That's a bad thing. But we can use the D to E at 25. That does not create a circuit. And so now notice we have a tree. All 5 of our vertices have been connected and we have not created any circuit. So when it comes to the weight of the minimal spanning tree, we are now going to add up all of those weights. So 15, 19, 24, 12, and 25, all the ones we highlighted, for a total of 95. Okay. All right, now let's do the same thing for this next graph. Okay, so here we have a botanical garden. They're putting in some displays and they need to irrigate. They need to run irrigation pipes, and it shows the distance in between the displays in yards. And so they want to do the minimal amount of pipeline because obviously that would cost the least amount of money. So how much pipe are they going to need? So again, we start by highlighting the edge with the smallest weight. That is the edge from Q to R with weight 8. The next smallest weight is U to P with a weight of 9. The next smallest weight is R to S with a weight of 11. Again, we're not creating a circuit. We haven't used any edge twice, so we're good to go, or any vertex twice, so we're good to go there. The next smallest weight is 15. That's not creating a circuit, going from P to R. Our next smallest weight would be 17, and notice that if we did do the 17, that would create a circuit U, P, R, Q, U, P, R, Q. So we don't want to include the 17. That's not going to be one to use. Oh, and actually, I'm just realizing before we even did that, before we did the 15, I missed a 12 in there. I didn't see the 12 from P to T. That happens actually quite frequently, so always be double checking. It's real easy to overlook one. So U to T, and then actually the 15 is our best deal. Our P to R And we don't have a circuit. So I apologize for missing that one, but again, I don't mind making mistakes for my students, whether it's on video or in person. Just shows you that I am human too, and you have to pay attention to what's going on. So adding up these weights, we've got a 9, a 12, a 15, an 8, and an 11. It's going to take 55 yards of this pipe in order to be able to irrigate all of their gardens. So that's what Kruskal's algorithm is all about.